So I'm Dr. Cameron Hummels, and I'll be the MC for tonight's event. Thank you for joining us at the Caltech Astronomy Stargazing Lecture, the last of the season. We will have them in July through the rest of the year. And I'll put out the announcements very shortly with our July dates and subsequent dates. Just in terms of what to expect for tonight, after a few brief announcements from me, I'll turn the microphone over to our speaker for tonight, who's going to talk all about space weather and its implications for, aurora, beautiful lights in the sky, as well as dangers to astronauts and telescopes above our atmosphere, as well as habitability on the Earth and in other stellar systems around the galaxy and the universe. So it should be very exciting and interesting. But we'll have that, and then we'll have a few minutes of brief Q&A with all of you, and then we'll have a sort of split, and there will be the opportunity to remain in here. We'll have a Q&A panel consisting of our speaker, myself, and two other members of the department who work on different areas of astrophysics, one who works on supernovae explosions, and one who works on the collisions of galaxy clusters, the most powerful explosions in the universe, who are going to be able to answer questions on all areas of astronomy and physics and space science that you may have. At the same time that our Q&A panel is going on in here, we have telescopes that'll be operating on the fields directly behind the building, and you're free to go out and look through those telescopes. We've got wonderful weather tonight, so you should be able to see a lot of cool things. For those of you just arriving, if you go out the other entrance, there's another door, and you may find more spots from this right side, or you can do exactly what you're doing and find spots in the back. So I think tonight we'll have good views of the Hercules globular cluster, which is a really cool star cluster in our own Milky Way galaxy, consisting of hundreds of thousands of stars that are bound close to each other. We'll have a good view of the Ring Nebula, which gives us an idea of what our sun is going to do when it reaches the end of its life in about 5 billion years, when it runs out of fuel. It won't turn into a supernova, but it'll end its life in a slightly different way. And this object, the Ring Nebula, gives us an idea of what that will look like if any of us live to be 5 billion years in the future, which I don't plan to, but modern science, who knows? So, and then the third object will probably look at the Whirlpool galaxy, kind of a galaxy that looks a lot like our own Milky Way, but it's at a distance and has some nice spiral patterns that makes it look a bit like a whirlpool. And then finally, the moon is up, so we'll have nice views of some of the craters and the structures on the moon. So I encourage you, if you want to look through the telescopes, find a time between 8:30 and 9:30 to 9:45 or so to go out and look through the telescopes. But you're also free to come back in here and listen to the Q&A panel, or go back and forth between the two. The doors will remain unlocked, and you're free to do whatever you choose. So, so that'll be our plan for the rest of tonight. And we'll go in here until about 10 o'clock and out there until about 9:45. These, as I mentioned, these events happen once a month on a Friday night. We've been doing them for almost 10 years, and they're always live streamed. So hi, YouTube audience. They're being live streamed on YouTube right now and recorded. So if you missed this, or you missed any of our previous ones, you can go back on our YouTube channel and find them and watch various different presentations on different topics, from black holes to galaxy evolution to space weather, like we're hearing about tonight. In addition, we have a related series of events that takes place in Old Town, Pasadena, called Astronomy on Tap. These take place at a bar called the Doghouse Beer Garden in Old Town, Pasadena. They are all ages, despite the fact that they're held in an outdoor beer garden outside of a bar. And they consist of two kind of 15 to 20-minute presentations, much like the one tonight, but shorter and more abbreviated, on different science topics. And then afterwards, there's astronomy-themed pub trivia, there's telescopes set up there as well, and there's live music from a local musician who comes and performs, named Jason Achilles. So those are all, like these events, free and open to the public. Our next one of those will be in a few weeks on June 23rd, Monday, June 23rd. And I haven't yet set the schedule for the rest of the season. The two talks that'll be given at the one in just a few weeks will both be about black holes. Both of the people giving the talks recently got their PhDs in astrophysics here, and study and try and use computer simulations to model how black holes behave in the presence of different conditions, sometimes a wind, or sometimes when you have merging black holes. And they're going to talk about both black holes as well as how we can model them on computers. So it should be pretty exciting. Other announcements. I guess I should mention that we will be helping out with a couple of dark sky festivals that are happening at national parks this summer, later this summer, that are, of course, open to the public and free. One will be at Sequoia National Park, just a few hours to the north in the southern Sierra Mountains. And that will be, I forget the exact date, but I think it's the first weekend in September. We've helped out the last few years at this one, but it consists of public level presentations on different science topics over the course of a few days, as well as, of course, telescope setup in some of the darkest skies in California. So I encourage you, if you're interested, check out the dates on that. We'll be there to aid in things, but it should be a really good time. The other event will be the week after that, and it'll be in Great Basin National Park, which is more of a drive from here. It's in Nevada. It's about a 7-hour drive, so it's kind of a ways. But the benefit is that it's amongst the darkest skies in all of North America because it's so far away from cities and towns and the light pollution that those cities and towns produce. I was just out there last weekend and was able to see the aurora, which we'll probably hear a bit about tonight. Because it's just really, really dark skies because there's like nobody out there, and it's really cool. So the Great Basin Astronomy Festival at this Great Basin National Park will take place I think the second weekend in September, and we will be out there assisting with that. So I just mentioned these things if you want to start booking or planning for visits to really cool sites that are fun. It's a good excursion to get outside of the city lights of Los Angeles. And finally, my last announcement before I move on to our presentation and our speaker is, you may have read in general, all of the events and the science that we talk about at these events is supported by federal taxpayer dollars, and we are greatly appreciative of those federal taxpayer dollars through NASA and the National Science Foundation and other federal agencies, the Department of Energy. Right now, the new presidential budget has cut funding for NASA, particularly NASA astrophysics and NASA science, by over 50%. And I don't want to get political here. I just want people to know the consequences of the budget cuts and what that will lead to. Certainly, these events will stop happening because they are supported through federal grants. I will not have a job in 6 months if these go through. But more importantly, the science that we talk about at these events will stop happening in the United States, and we will lose our stature as basically the preeminent location in the world where science is done. It will primarily move to Europe and China. And that's not to try and get political. That's just to say the logical consequences of those cuts. So if you feel strongly and want to support federal support for the sciences, I encourage you to reach out to your representatives and express your opinions that we need to support federal dollars for science to be done in the United States to retain our position as the primary science dealing nation in the country, or in the country, but also the world. Okay. And I will, in the next week, put some sort of script and directions in case people want to reach out to their representatives and are a little bit anxious about dealing with that. I'll provide a script for what you might want to say, but you can obviously change it as you see fit. Okay, so now on to the science. Our speaker for tonight originally hails from Alabama. They did their undergraduate studies at University of New Mexico in astrophysics and physics, and then joined the department here at Caltech as a graduate student 5 years ago, and is now a fifth-year PhD student and will be defending their PhD in just a couple of months, after which they will go to a famed radio astronomy institution in the Netherlands and Europe to conduct this same research that we're going to hear about tonight at Astron, this Dutch astrophysical institute in Dwingelo, the Netherlands. They have such cool names for their towns there. But their research that they've been working on is all about, as I mentioned and alluded to, the evolution of the sun and how variability, both in terms of radiation, but as well as particles that are streaming off the sun, affect things here and other places in our solar system. And they've done some really groundbreaking research, both using radio telescopes as well as commissioning and building their own optical telescope to study the evolution of our sun and how it's changing in this way, as well as other star systems that are changing that might give us a clue as to how our sun may behave in the future or behaved in the past. So please welcome our speaker for tonight, Ivey Davis.
Thank you. Thank you, Cameron, for that introduction and also inviting me to do this. And thank you all for coming. I'm super stoked to talk to you all about the sun. To start, I wanted to begin with a brief introduction to the history of how we've studied the sun. We've known about it for quite a long time. And so we've been studying it for about as long as we've been studying anything. And in particular, even thousands of years before the invention of the telescope, we've been studying changes on its surface. Some of the earliest reports that we have of these changes come from the Chinese Book of Changes that date back all the way to 800 BCE, so about 2,800 years ago, which is pretty phenomenal. Now, I said that this was happening before the invention of the telescope, and the way that they were studying the sun is actually pretty similar to how we like to look at solar eclipses today, which is through something like a pinhole camera or through the camera obscura phenomenon, where you have a really tiny hole in, here it's a piece of foil. I don't think they had foil 2,800 years ago, but you poke a tiny hole through a medium and that projects the image of the sun onto a plane far away. Now, what may be obvious from this is that the details you're going to be able to see on the solar surface aren't that great. What they were really seeing were smudges, but very clearly smudges or peculiar features, dark features on the sun's surface. Things really started to gain traction and we started to really understand what was happening on the sun's surface through some improvements in the camera obscura method, but also with the invention of the telescope over 2,000 years later, or yes, almost 2,000 years later in 1612. And here what I'm showing is one of the first drawings of the solar surface using a telescope as made by Galileo. And what the telescope started to show us is that these sort of bloppy, fuzzy features, these dark features we were seeing on the sun, actually had some pretty significant structure to them. It's not just that the sun had some dark, fuzzy regions, but that there's actually structure. These were individual spots and blobs happening on the surface of the sun. And with the invention of the telescope, we not only got to resolve those structures, but more effectively study how they change in time and also how they change based on their position on the solar surface, actually. Now, another major sort of change in our understanding in how the sun changed came about 200 years later in 1859 through the studies done by Richard Carrington in England. And what I'm showing here are some sunspots that Richard Carrington was observing, some fun, blobby, sausagey structures, but also what Richard Carrington observed for the very first time, as far as we can see from solar records, are these brightened features. We were used to the sun having dark features moving across its surface, but this was the very first time we ever had records of the sun getting brighter. And we know now today that what Richard Carrington was observing was solar flares. These were the first recorded solar flares, which is pretty exceptional, right? We don't usually see a hot surface get even hotter. Now, things got even more exciting a day later here on Earth when we witnessed telegraph stations catching fire and also aurora visible down to extreme latitudes as far south as Hawaii and Cuba. And we now know today that the flares that Richard Carrington was observing is connected to the aurora, the geomagnetic events that were observed here on Earth. Geo referring to the Earth and magnetic referring to magnetic field-driven phenomena. And we, as astronomers and solar astronomers and stellar astronomers, consider this sort of the start of space weather studies. And I want to emphasize the aurora I'm showing here is not from the Carrington Event. Cameras weren't quite that good yet, but this is from just a year ago from Southern California, the aurora we were observing due to the geomagnetic activity happening due to the sun then. And so we like to use the Carrington Event, as we now call it, as sort of a benchmark. We're always referring to it as solar and stellar astronomers, both because it represented the start of our understanding of space studies, the sort of impact that changes on the sun has here at Earth, but also because it was exceptional. There's a reason that was the first time we saw the first solar flare. It was an extremely energetic event. And if it were to happen today, it could cause trillions of dollars worth of damage to the electrical grid and the infrastructure we have set up today. And so because of that, we have invested a lot of time and money and science and mental capacity to trying to understand the sun. And in particular, we have had a lot of different instruments go up into space around the Earth and around the sun in order to understand what is happening on its surface, what's happening in the time between when a flare is observed on the sun and when we experience a geomagnetic storm. These are a variety of missions. I think all of the heliophysics missions that NASA is involved with. Now, as Cameron mentioned, unfortunately, there are significant budget cuts happening to NASA right now, and these are the missions that are slated to be decommissioned, or if these were planned missions, they are slated to never happen. And I want to emphasize that understanding how the sun works and what that means for the Earth is very important for understanding, especially as a very electronically driven civilization. It's important for understanding how we prepare for these events. So it is truly detrimental to lose instruments like this that are dedicated to understanding the sun and its impacts. But I won't spend too much time belaboring that point. Let's talk about space weather and what we have learned from these missions about what's happening on the sun and what that means for us here on Earth, how we forecast the space weather happening at Earth. To start, let's consider the sun. This is an image of the sun's surface that was taken just a couple of weeks ago. And what may be obvious are these sort of dark features on it. Those are those sunspots that we've been observing for thousands of years. And it's easy to lose perspective when you see an image like this, but the sun is much bigger than the Earth. This is an image of the Earth for scale next to one of these sunspots. They are truly massive, at least by human standards. And if you want to learn more about this particular group of sunspots or an active region, I have a QR code here, which hopefully the resolution is good enough to scan it, that'll tell you more about this specific sunspot through the Space Weather Network. Now, these sunspots are regions of exceptionally strong magnetic fields, so strong that they prevent material, hot material from deep inside the sun reaching the surface of the sun. And because that hot material can't reach the surface, the area appears cooler and thus darker. Now, that magnetic field that is so strong to create such a big spot extends out into the outer atmosphere of the sun into the region that we call the corona. This is the outer atmosphere. And I won't get into all of the nitty-gritty details of what's happening in the sun's atmosphere because it's a bunch of magnetic shenanigans. But in essence, what happens is that the coronal magnetic fields can get tangled up. And just like how when you twist a rubber band or if you tighten a violin or guitar string, you're going to build up tension in those strings, in those fields. And I don't know if anyone has ever been struck by a violin or guitar string just snapping under the tension, but it hurts. And these fields are the size of the sun. So when you build up that tension high enough that they're actually able to snap, that is a lot of energy that you have stored in these strings, in these fields. And when that energy gets released, that's what we observe as flares. You're heating a bunch of material within the corona that can go all the way to the surface of the sun. And this is what Richard Carrington observed. He observed flares. Now, in the instance that these flares are energetic enough, then you can actually accelerate particles. You're not just heating the particles, you are pushing them outwards. And this is what we observe nowadays as a coronal mass ejection, or CME as I have it labeled here. And actually, nowadays, we are very fortunate that we have technology that we can directly image these coronal mass ejections. So what I'm showing here is a video of the sun. It's out of atmosphere, the corona, and all that material blowing outwards after a massive flare. And I want to reemphasize that also that black disk is the surface of the sun. And if you remember, the Earth is much smaller than the sun. And so all of that material blowing outwards is truly massive by the sort of standard scales that we have here on Earth. There's a lot of material in that corona that the sun is blowing outwards towards us. And thankfully, we do have these direct images of coronal mass ejection. So we get a good sense of when it's heading our way. And in the instance that it is heading our way is when we start to get a little bit worried. That's a lot of very energetic particles, tangled magnetic fields that are going to interact with our atmosphere, with us here on the surface. And that's when we start to get a little bit concerned. That said, we also get to see pretty things like aurora. So what I'm showing here is actually an image of aurora taken in Tasmania just this past weekend. The sun is being super active and bonkers right now that we get to see pretty aurora like this. But we have to take precautions because this does have impacts for us here in a meaningful way besides just getting to see pretty events. And I wanted to take a moment to talk a little bit about how aurora work, both because I think they're cool, but also because the history of our understanding of aurora is actually tangentially related to Caltech. So to start, we have the Earth here. We are somewhere on there. And one of the fun things about the Earth is, like the sun, it has an atmosphere. And also, like the sun, it has a magnetic field that is interacting with that atmosphere. And also, like the sun, we have launched satellites into it. We have the ISS, the International Space Station. We have a bunch of GPS so that we know where we're getting around. We have a bunch of communication satellites. We have a bunch of satellites up there that sort of rely on the magnetic field to protect it. And the reason it relies on the magnetic field to protect it is because, contrary to popular belief, space is not a vacuum. There is, in fact, a whole wind coming off of the sun that is interacting with the Earth's magnetic field. I have it indicated here as orange lines with arrows indicating the direction, but I'm sure lots of people have seen like a video or witnessed a dog like sticking its head out the window and like the wind blowing it back. And just like how the wind here on Earth will blow back a dog's ears, the solar wind will blow back the Earth's magnetic field and distort it. Now, this is happening all the time. The sun is always blasting us with a solar wind, which is why we can pretty regularly see aurora, at least at high latitudes. Now, in the presence of a coronal mass ejection, or CME, that wind ramps up. It's like if you're driving with your dog at 20 miles per hour and then blasted it at 120 miles per hour, it's going to really distort that dog's ears. And it's really going to distort the Earth's magnetic field. So much so that you can actually snap the Earth's magnetic field lines, similar to how you might snap the sun's magnetic field lines to produce those flares. And just like how those flares can accelerate particles, these snapped Earth magnetic field lines can accelerate particles so that we get even more extreme auroral events. All of the particles from the sun's wind are going to be deposited into our atmosphere, interact with our atmospheric chemistry to produce these fun auroral events. Now, another consequence of this is that all those satellites that we have out in space suddenly lose their shielding of the Earth's magnetic field, which poses an interesting problem both in terms of electronics. We can have GPS blackouts in these instances, and also the folks that live on the International Space Station get a little bit worried. And I wanted to talk about this in particular, again, because the person or one of the people that played such a huge role in our understanding of how the solar wind and coronal mass ejections interact with the Earth to produce these aurora is actually tangentially related to Caltech. And I wanted to take a moment and see if anybody wanted to guess or if they know who this person is that I'm talking about. So does anybody want to say? Yes? It was not Einstein, but great guess. Anyone else? Yeah. Very close. Someone related to Feynman. Do you want to take one more guess? That's okay. The person who described the interaction between the solar wind and the Earth's magnetic field was Joan Feynman, Richard Feynman's younger sister. Fantastic guess. And she played a truly integral role to our understanding of coronal mass ejections and the solar wind and the impacts that they have here for us on Earth. In particular, again, she described their role in the production of aurora, but also she was doing this science during a time we did not have all of the satellites or a fraction of the satellites that we have now in order to directly image coronal mass ejections. She was making incredible derivations based on changes in the composition of the solar wind in order to tell whether or not a coronal mass ejection even occurred. And to this day, we use the sort of formulation that she came up with to understand what the wind and coronal mass ejections means for the lifetime of spacecrafts up in space. This is how we predict how long we can actually continue to do the missions that we do. And after she retired, she continued to do science, but after she retired, she stopped focusing so much on electronic impacts, but started investigating the ways that the winds and coronal mass ejections impacted the long-term Earth-based climate. So she did quite a phenomenal slew of work. Not just that, but also socially, she did a lot of work. She created a committee in order to try and improve the experience of women in geophysics. Joan Feynman herself, when she was doing her undergraduate, would not have been able to attend Caltech purely on the basis of her gender. And she experienced a variety of hardships as a woman navigating astronomy and physics. And I have another QR code here that hopefully you can scan that links to an article written by her son that goes over her experience both as Richard Feynman's younger sister, but also more in detail on her experience as a woman in physics and trying to make physics and astronomy a more accessible place for everybody. And to conclude this slide, I wanted to leave y'all with a really fantastic quote from her, which is, "How could I retire when the sun is doing such crazy things?" Which I like to believe that this is a sentiment that most astronomers have about their science. It is truly a passion project, and we are so lucky that we get to study the fantastic things in the universe that we do. So thank you for humoring that tangent about Joan Feynman, but let's get back into space weather. In particular, let's take a look at what that coronal mass ejection that hit the Earth is going to do to the other planets in our solar system. So here we are back with the Earth and its magnetic field that is shielding us from its coronal mass ejection. But that coronal mass ejection keeps going, and as it keeps going, it is going to encounter Mars. And Mars, as I am presenting it here, is Mars as it was 4 billion years ago, which is to say, it probably had oceans. We have deduced from its surface features that Mars likely had rivers, lakes, oceans, all these fantastic bodies of water, which implies a water cycle, which in turn implies it had an atmosphere. Now, unfortunately, Mars probably lost its magnetic field exceptionally early. So this means that that coronal mass ejection that's heading towards Mars isn't going to be deflected by the magnetic field like it is here on Earth. It's just going to directly interact with its atmosphere, and then eventually it's going to directly interact with its surface. And so as it goes by, it's going to strip away the atmosphere of Mars, leaving it as we see it today, which is a planet with essentially no atmosphere, no water, very likely uninhabitable. Which all this is to say that the sort of properties of the planet actually plays a really exceptional role in the idea of habitability. But we also know that our sun is one star among billions in our galaxy. So let's take a moment to talk about how stars and their features impact the idea of habitability and space weather. And in particular, not all stars are like the sun. Sort of the main ways we like to characterize our stars are based on their sizes and their temperatures. So what I'm showing here are just some images of some various stars where we have the biggest and the hottest up top, and we have the smallest and the coolest at the bottom. And another way, at least a way that I like to characterize stars, is based on their ages and their activity, their magnetic activity. And just like how folks tend to get less active as they get older, stars, as they age and get older, tend to be less active. That said, the way we usually like to characterize habitability is based on the size and the temperature of the star. This informs what we call the habitable zone. Now, more specifically, the habitable zone is the region where a planet could sustain liquid water if it had an Earth-like pressure. A very nuanced definition that gets lost in popular science media, but that is the definition. And in particular, for a star like the sun, we might say that the habitable zone is right around there. That's where the Earth is. That's where liquid water exists. But for these bigger, hotter stars, they're putting out a lot more radiation, a lot more flux. They're way hotter. And so, like how you might need to step away from an oven that's hotter, you're going to need to put your planet further away in order for liquid water to exist. If you put it too close to the sun or the star, then you're just going to evaporate all of that water. So the habitable zone moves further away for those hotter stars. On the other side of things, we have these small cold stars that we like to call red dwarfs. And because they are so small and so cold, if you want liquid water to exist, you've got to put your planet really close by. Otherwise, your liquid water is just going to be water ice, right? It's going to freeze if you're too far away from your star. So this is what we call the habitable zone, the region where liquid water can exist. Now, this poses some really interesting questions in terms of habitability because the most common star in our galaxy, in the universe, are these small cold stars. So the habitable zone is going to be really close to their surface. Now, the other caveat here is that these are also very long-lived stars. They are so small that they go through their fuel that keeps them living really slowly. So they live for billions of years longer than our sun does. And because of this, they also stay active for much longer than our sun stays active. And to put this into a little bit better scale, let's actually go back to the solar system. So what I'm showing here is the inner solar system. There's our sun, and then our inner planets, Mercury, Venus, Earth, and Mars. And the habitable zone is indicated here by the green regions. So we see that Earth is about smack dab in the middle in the habitable zone. And Venus and Mars are sort of teetering on the edge based on the numbers that you use. Now, there's this itty bitty region indicated in the inner solar system where the TRAPPIST-1 system lives. TRAPPIST-1 is a small red dwarf, a very itty bitty cold star, and it has about several planets orbiting around it. And notably, several of these planets actually exist within what would be called the habitable zone for this star. But all of these planets exist within the orbit of Mercury around the sun. These planets are so exceptionally close to their host star, which, good, they should have the right temperature to host liquid water. The problem is when you start to incorporate details like activity. In particular, these flares happen relatively close to the solar surface, but even relative relatively close to the stellar surface for a star like TRAPPIST is basically right at the location of these planets. So they're just getting absolutely bombarded with UV radiation, X-ray radiation, ionizing radiation that we consider pretty detrimental to life here on Earth, at least causing significant mutations and driving incredible chemistry that is beyond the scope of this talk. The other thing is that TRAPPIST-1, not only is it putting out flares like this, but it's putting them out way more often. And these flares are way more energetic than any flare we've ever observed from the sun. And this is just to talk about the radiation of the flares. This says nothing of the particle flux that is hitting these planets. In particular, flares of this scale are going to produce, presumably, events orders of magnitude stronger than the Carrington event. Again, an event that we consider one of the strongest, if not the strongest, solar event in recent history in the past 1,000 years or so. And to sort of visualize this, I wanted to include an animation of what the solar wind looked like during the Carrington event. And then I want you to try and scale that up by a factor of 100. So there's a wind, and then there's the Carrington event just absolutely obliterating the Earth's magnetic field. Now imagine you're 10 times closer to where the event originated, and also the event is 10 times stronger. That planet's magnetic field does not stand a chance at protecting it. And so understanding the particle flux, the space weather coming from these stars is crucial to understanding what it means to be habitable, to be in the habitable zone. Unfortunately, although we can study the flares from these stars pretty effectively, we have been for decades, understanding the particles is way more difficult. Here on Earth, we're lucky. We get to see the particles from the sun hit us. We get to see the aurora that happened because of that. But for these other stars, we don't see the particles. We have to infer what's happening from here. Thankfully, there has been an ongoing effort here at Caltech through the Keck Institute of Space Studies in order to try and understand what is happening during these flare events, the particles that these stars are producing, and what that means for habitability. In particular, there has been a fantastic group of scientists coming from solar backgrounds, from stellar backgrounds, from planetary and exoplanetary backgrounds in order to understand what is a flare, what is a particle, and how do those flares and particles get accelerated, and what does that mean for those planetary surfaces, the chemistry that's happening there, and what does that mean for habitability? This is a really exceptional field of study that's experiencing a lot of growth right now, and I'm super excited to say that by the end of the year, there will be a fantastic report coming out from this group that summarizes the findings, both what we already know about space weather here in the solar system and what we can learn and what we hope to learn from future missions studying other stars and what that means for us here on Earth. So to conclude, I wanted to leave you with this really fun video we have of the sun that came just a couple of weeks ago. This is the solar surface, and we can see the magnetic field containing those hot material, those particles. And what we're witnessing here is coronal rain, a great way to end a talk about space weather. The sun does rain, it's just not water rain, it is hot plasma. Don't go to the sun. This is all just to say that the sun is really weird. We've been studying it again for thousands of years, about as long as anyone can study anything, and there's still so much to learn about it. And part of the way we learn about it is through studying other stars, but other stars are even weirder. They're doing a lot of fun stuff, and we're sort of limited by the instrumentation we have available to study them. And so having these missions that unfortunately are at threat of being lost, that were either in the works or have been operating for decades, are under threat of being lost. And that means a lot for both our understanding of our history here on Earth going back billions of years, but it also means a lot for our capacity to predict what's going to happen to us in the future, right? We don't want a Carrington event hitting us, or at least we want to know how to handle things if it does. So this is to say also that this weirdness is critical to our understanding of habitability. So with that, thank you all for your attention.
So we can take a few questions from the audience. Is there any questions for Ivey?
If Venus is in the zone of habitability, how come it's not habitable?
That is a great question. Thank you. So the question for those online is, if Venus is in the habitable zone, why is it not habitable? There's actually a couple of nuances to this. The first is we don't really know the exact numbers of the habitable zone. It might just be right outside it. The other thing is that Venus is really weird. Venus has a really slow rotation, and I think it's actually retrograde orbit, which means that its rotation is actually, it takes a day on Venus is longer than its year around the sun. It is very peculiar. And all of this has weird implications for its capacity to generate a magnetic field. It doesn't have a magnetic field, but also it has weird implications then for sustaining an atmosphere. Notably, Venus has a really, 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 really thick, dense atmosphere. So even though it's getting blasted by the sun, there's just so much material there that it holds on to it really well. So the idea of habitability for Venus in particular is really weird, although there have been papers in recent years that suggest there are signatures of habitability, but that depends on the astronomer you believe.
Additional questions? Yeah.
Hi. When the solar flare, I don't know if penetrates the right word, but if it goes through the Earth's magnetic field, does it destroy that portion of the magnetic field, or just kind of blows through it? And if it does destroy it, does the magnetic field regenerate or come back once the event is over?
Yeah, thank you for that question. The question was about what is happening to the Earth's magnetic field in the instance of a flare or a coronal mass ejection. Is it destroyed? And if it is, does it come back? And what's happening to the magnetic field is that it is breaking in some respect. We are snapping those lines, but the overall magnetic intensity of the Earth is preserved. And one of the reasons it's preserved is because the Earth has really interesting internal dynamics that does continuously generate a magnetic field. So even in the instance that a magnetic field from the Earth is blown away, so to speak, as I presented it here, it does regenerate it actually.
Right. I assume that solar flares and particles has an effect on the size of organic molecules. And I wonder if there's a size, chain length, things like that would reflect the history of where those organic molecules could have come from.
That is a very interesting question. So the question for those online was whether the sort of particular details of flares and coronal mass ejections has an impact on the size of organic molecules. And I'm not a chemist, and astronomers are famously very bad chemists. Everything heavier than hydrogen is a metal. It's that said, I will say what I do know about chemistry relative to the sun is that there is a preference for the chirality or the handedness of organic particles. So there is a preference for the orientation of particles, presumably due to the particle flux we see from the sun. How you can prove that, unclear. But that is a thing that we observe is a preference for the orientation of molecules. And that seems to be aligned with the orientation of particle flux we see from the sun.
We can take two more questions and then we'll break for our Q&A panel. There's a question back here. Wasn't there a question back here? There's a question. But hold on just a second.
I was just wondering about your work on Flarescope. I read a little thing about it. I just wanted to know more about it. Just how it's works and how it's really interesting, autonomous. So
Yeah, thank you. For those online, the question is about the instrument that I designed and built, Flarescope, which I designed and built specifically to study activity flares on sun-like stars. I won't get into all the details on it, especially since there is a paper that will be coming out soon that goes into all the details of it. But it's a small telescope and it's up actually at Palomar Mountain. If anyone's ever visited the Hale telescope, the 200-inch telescope, or if you've heard about Zwicky Transient Facility, it's at the same location as those telescopes. Uh, it's a really fun instrument. It's fun detail about sun-like stars is that they are very bright, which actually makes them harder to observe in some respects. So Flarescope was designed with the peculiarity that it can actually observe this brightness to a precision that even telescopes like the Transiting Exoplanet Survey Satellite TESS can't quite observe because these stars are so bright. I could go on for hours about it, so I'll stop myself there.
We can talk about it during the panel Q&A afterwards in more detail. Okay, one more question.
How many bands are expected to work? How many bands snap during the Carrington event?
Ooh, the question is how many bands were snapped during the Carrington event? And that's a great question that I don't know the answer to. But if I understand what you're referring to is that the Earth's magnetic field is referred to in like L sequences or based on the number of Earth radii that you are. From the animation that I showed, it seemed like most of the bands were snapped. But yeah, I don't know off the top of my head. Sorry about that.
Okay, let's thank our speaker one more time. Thank you, Ivey. And so now what we're going to do, we'll have a brief intermission in here while we set up the Q&A panel, which will be operating for the next hour or so in here. If you'd like to go look at the telescopes, they're now set up outside. If you go outside the front doors that you came in and come around this building, follow the signs, it's about a couple 100 feet behind me. The telescopes are operating and for another hour or so. So feel free to come back and forth between here and there if you wish. And otherwise, we'll see you at our next event in a few weeks, Astronomy on Tap, June 23rd, about black holes. Okay. Thank you for all of you who stuck around for our Q&A panel, astrophysics Q&A panel. What we'll do is each of us will go through and give a brief 30-second introduction to each of us and the science that we work on. You're, of course, welcome to ask questions on whatever you want to. I mean, related to astronomy and space science and physics. Even if it's not a topic that we say we're a specialist in, we know more than the average bear. We can try and deduce some sort of answer. And we've got some members of the department who are in the audience who can throw in some help too. So I'm Cameron Hummels. I'm a research scientist here. My research focuses around understanding galaxies like our own Milky Way and how galaxies form and change over their lifetimes, which last for millions and billions of years, so much longer than the timescales that you and I probably experience. I can't speak for you, but I can speak for me as being much shorter than billion-year timescales. And I do that through using supercomputing simulations to kind of follow the evolution of galaxies on those long timescales where we can artificially speed up the simulation so it covers a much longer timescale than it would otherwise if we were just sitting around waiting for galaxies to change and evolve.
Hi, I'm Ivy. I just talked a lot about what I study, but I study solar and stellar magnetic activity. And in particular, I study other stars that are like the sun, but at a much younger age in order to sort of understand what that could imply about how the sun was acting when it was much younger, and in particular, how it was acting when life was first forming here on Earth.
Hi, I'm Maggie. I work on supernovae, specifically massive stellar explosions, and what that could mean for like stellar structure, how supernova can enrich their environments, and other emission mechanisms that accompany supernova explosions, like gamma ray bursts.
Hi, everyone. I'm Emily. I'm also a grad student at Caltech. I study the most energetic events in the universe. So specifically, these are collisions between massive clusters of galaxies. And because collisions between massive clusters of galaxies are so energetic, they emit radiation all across the electromagnetic spectrum, which means I get to use telescopes all across the electromagnetic spectrum to study them. So I use X-ray telescopes, optical telescopes, radio telescopes, and I combine all of that data, all of those observations with predictions from computer simulations like the ones that Cameron runs in order to understand these massive structures.
Okay, so now we take questions from both you as well as our online YouTube audience. They're watching this as well, hi YouTube audience. So if you have questions, raise your hand and I'll call on you, and then we'll try and do what we can.
A question for Ivy. You described the situation and the effect of the space weather of the sun on the Earth. I wonder what is the state of the art of looking at the effect on the moon. The moon has no magnetic field at all. It is locked to the Earth, so it looks at the sun, or the sun looks at it for a longer period of time, and we're going to put people on the face of the moon. So what's going to happen?
Yeah, that's a really great question. For those online, oh, okay, perfect. Never mind. So I don't actually have a great grasp of the effects of space weather on the moon. As you said, it doesn't have a magnetic field. It doesn't really have an atmosphere. So any particles coming from the sun and any radiation are going to directly impact the surface, which is very dangerous, especially if we want to put a colony on the moon. I will say there has been increasing discussion of putting telescopes, irrespective if there's a person there to man it, on the moon. In particular, Greg Hallinan here at Caltech is interested in Farside, along with his postdoc, especially Nivedita Mahesh, in putting a radio telescope on the far side of the moon. And I'm sure they have probably put a lot more thought into the impacts of the radiation and the field that comes from that.
One thing I want to add is I agree with everything that Ivy said, but one additional thing is that So the solar wind particles that are coming off the surface of the sun and they're traveling into the outer solar system. And of course, as Ivey discussed in their presentation, our Earth's magnetic field is a shield that kind of blocks those particles from directly impacting the surface of the Earth. But the moon, without a magnetic field, those particles impact the surface. And one of the outcomes of this is that they bombard some of the hydrogen atoms there, and they cause what's known as what is it? Is it spallation? Sputtering, where these particles impact hydrogen atoms and they actually bind with them. And so you end up with heavier isotopes of certain elements or different isotopes of certain elements. So for instance, if you think back to your days of chemistry or physics in high school and you think of the periodic table, right? There's hydrogen and then there's helium, which is the next heavier element. And most helium, the most standard helium isotope that we have, has 2 protons and it has 4 neutrons. No, two protons and 2 neutrons, right?
Helium?
Yeah.
Yes.
Yeah. So it has an atomic weight of 4 and an atomic mass of 2. So it has 2 protons and 2 neutrons. But you can have an isotope. Isotope is just a fancy word for a different number of neutrons on that element. You can have helium-3, which only has it has 2 protons and 1 neutron. And it turns out that there is more of that on the surface of the moon because these free-flowing particles are coming off the sun and they're interacting with hydrogen. And essentially you get hydrogen and some, you end up forming more helium-3 than you otherwise would on the surface of the Earth. And you're like, who cares? Who cares about helium-3? That's no big deal. But one of the things that's important about helium-3 is that it can be used as a fuel for nuclear fusion. And it turns out that when you use nuclear fusion is what we'd like to be able to do here on Earth to produce clean energy, or one of the ways we'd like to produce clean energy in a lab where you confine nuclei, you smash them together and they release energy. So you could take like hydrogen atoms, smash them together, release energy. And this is happening in the interior of the sun. This is what powers the sun. But we'd like to be able to do this here on Earth, and it would, it'd be a much cheaper form of energy if we could get things going with very, unlimited fuel sources, because it's just hydrogen, which is in water and all the things. But also it doesn't produce a lot of bad outcomes. So, but to find this fuel, you have to go to the surface of the moon to get it in much more enriched stuff. And so this has been the premise of certain science fiction books and movies. You may have heard of a movie that came out about 20 years ago called Moon. It's a pretty good movie. And it's all about a helium-3 farming mine on the surface of the moon in the distant future with this promise. So that was a really long-winded explanation, but helium-3 is in higher abundance and it may be a fuel for a certain kind of lower cost, lower impact nuclear fusion. And you can get it there, and it's as a result of the solar wind interacting with the surface of the moon. Okay, that was a lot to say. Additional questions. And also I've gotten feedback from people that sometimes people hear questions here and they think, oh, I'm gonna sound dumb if I ask that question that I actually want to know the answer to, but I don't want people to know that I don't know the thing. Don't feel that way. All questions are valid. There will be no judgment up here, no judgment out there. So ask your question, even if it's something like, why is the sky blue? Or why is the sun yellow? Or why does our Milky Way look like a band of light across the sky? Like, ask whatever you want, no dumb questions, and we'll do our best to explain whatever we can. And that was a great question too, sir.
I'm not sure who would know the most about this, but in Interstellar, when they go to the planet that's orbiting the black hole, is there even a zone of habitability near a black hole? And if so, would you actually get that like effect, like the time travel effect, where they only think they're on it for like a few minutes, but then it's been like 47 years or whatever when they get back?
Who wants to talk about time dilation? Who wants to talk about the energetic environment around a black hole? Do you think you'd get a lot of solar flares near an accretion disk of a black hole?
I feel like I need Jean up here for this.
Yeah, Jean. Jean, you want to come up and talk too? Yeah, come on up. We've got an additional supplementary member of our Q&A panel. Have a seat,
Recent
Jean.
PhD.
Recent, yeah, as of Wednesday, defended her PhD. Dr. Jean Samowar.
Thank you.
Here, have a seat.
Yeah. No, I mean, it's fine.
You sure?
Yeah. So admittedly, I've committed the cardinal sin if I haven't seen Interstellar, so I can't comment on the direct scene. But I will say, near a black hole, there's a lot of really, really crazy things happening. I would, as crazy as, if not more crazy than the sun. No shame on the sun, of course. So actually, I gave a lecture here a while back on things happening around black holes, what happens when you put gas near a black hole and things like that, and it starts to consume it. And as things get close to a black hole, you get a ton of crazy effects. So Cameron mentioned accretion disk. So basically, as matter falls onto a black hole, you get this really friction, like very hot gas close to the black hole is slowly falling in. In that gas, a ton of things can happen. You can actually have supernovae, like what Maggie studies, where you have stars exploding. You have, giant flares of light as the gas falls into the black hole, and that will, I would guess, absolutely destroy any planet that's anywhere in the vicinity. Now, I'm guessing that the black hole in the movie didn't have an accretion disk, or did it? I don't actually know.
That's a good question. If you guys, for those of you who've seen the movie Interstellar, maybe some of you haven't. Spoilers, but the movie came out a while ago, so sorry, I don't feel so bad. You think of the image of the black hole, there's the black circle, and then there's kind of the glowing region around it. That glowing region is what we call the accretion disk. That's stuff that's falling onto the black hole. And as it falls onto it and gets close to it, it heats up and it gets really, really hot. And these are some of the effects that Jean is describing are the radiation signatures of this sort of thing. So yeah, it has a small accretion disk, but it's certainly enough of an accretion disk that you wouldn't want to be there because there'd be X-rays and UV flying around and it'd be a bad place.
Yeah, like these are some of the most luminous objects you'll see in the entire universe. They're the way we first found out, like the first black holes we really knew about were the really, really far away ones because they produce so much energy that you can see them. At Caltech, a lot of this work was pioneered studying these black holes that are 1 billion times the mass of the sun in very, very distant universe.
Known as quasars.
Quasars, yeah.
Yeah.
And so their early observations of these were taken here, and that's where they was realized that these had to be black holes because they were so massive, so energetic, despite being so far away. So yeah, I wouldn't want to be there. Yeah. Even if you could somehow have a planet there, I wouldn't recommend it.
Yeah, I totally agree. And the part of your question about the time dilation effect, that's the stretching of time because, we think about time as being this independent thing that's just flowing forward and we're moving through in it like a river is flowing and it's uncontrollable. But one of the implications of Einstein's general relativity is that space and time are intrinsically linked. And so your motion through space will impact your motion through time. And when you're really close to a massive object like a black hole or even the sun, time will pass at a different rate than it does, a slower rate than it does when you're far away from a massive object. And so that's effect that occurred in that film, and that is accurate. That's an extreme example that time would pass for like an hour and then be like 17 years outside of that regime, but it is physically consistent. It is physically possible.
And just a quick note on that, actually, one of the first tests we have, if not the first test for general relativity we have, is the change in Mercury's orbit around the sun, because the sun's gravitational field imposes this sort of dilation effect, and it causes Mercury's orbit to precess with time. So it happens.
Thank you, supplementary Q&A panel member, Jean. Okay.
Actually, can I add something?
Yeah, please, Emily, go ahead.
Great. So this is pertaining to the first part of your question, which was about planets and habitability around objects that are not necessarily like the stars that Ivey was talking about in their talk. And actually, the first planet that we ever discovered outside of our solar system was not discovered around a star that emitted light. And neither was the second or the third, actually. And so these were discovered around another structure that's formed when stars die. So the most massive stars will collapse in on themselves and they'll form really massive black holes. But less massive stars will actually collapse into these really dense objects that no longer emit light, but they're called neutron stars. So they're extremely dense objects. I think I once heard the fact that a teaspoon of a neutron star weighs the same amount as Mount Everest. or something like that. And so the first couple planets that we ever discovered outside the solar system were discovered around these neutron stars. And these neutron stars were emitting crazy amounts of like X-ray radiation that would be absolutely detrimental to habitability, even though the sizes of them were much smaller than the stars that we often see planets around. So there can be planets around really interesting objects, and it's, the gravity of that central object that keeps them in orbit, but, it's things like light from the sun and heat that can sustain life and things like that.
Okay. Additional questions? Yes. Let's see. But you already asked a question, so maybe I'll hold off. Yeah, I'll hold off. I'll come back to you. Additional questions. Okay. Gotta conserve the questions here.
During your presentation, you showed a slide of all like the satellite that's being canceled. Are those like projects that's not going to be built ever, or they're already there, but then they're not going to be serviced anymore, or what's going to be lost because of these projects not going to be happening anymore?
Sorry, I missed the first half of your question. Which?
When you show your presentation, you show the slide with like the canceled projects.
Oh, the canceled projects. So these are projects. So the true effects of the new budget are yet to be manifest. Some of those projects that were canceled or slated to be canceled, I should say, were projects that have been operative. So things like ACE that are PI'd by people here at Caltech. They were projects that were done in collaboration with other institutions like those in Japan. And they were projects that were in the process of being designed imminently to be launched. So they represented a huge slew of persistent science that was happening, that was important, and science that would have changed, revolutionized the way we understand the sun's activity.
But it's true not just for heliophysics and the study of our sun, but also astrophysics missions as well, and planetary science missions. So right now, in reading over the budget cuts and if they go through as they're currently slated to do, what missions will be canceled? The Chandra X-ray telescope, which has been up for 20 years and 25 years and operating very well, that will be canceled. The gamma ray telescope will also be cut. So existing telescopes that are kind of in their extended lifetime, where it costs very little to continue to operate them, because it's like, if you're going to build a car from scratch, it costs a lot to build that car, but once it's built and running, it doesn't cost a lot to maintain it. It's the same sort of thing with space missions. They will continue to operate Hubble Space Telescope and James Webb Space Telescope. They would kill new telescopes that are in development now, like the UVEX telescope, which has already been, it's actually being built here at Caltech. It's a UV-based telescope that was meant to launch in the next 5 years. So that gets canceled. Prima gets canceled. A number of other large-scale missions will be canceled. So it's, yes, Parker does survive. So I think there's a handful of missions that are continuing, kind of high-profile missions that are continuing with the budget cuts, but they describe it as leaning the budget and focusing more on certain aspects. But notably, all of their education budget is like 95% of it is cut. So these sorts of events, not just here at Caltech, but I mean like NASA doing education will stop entirely. So yeah, it's not great. Oh, LIGO, the LIGO instruments that were detected the first gravitational waves from distant black holes, and the 2017 Nobel Prize in Physics to Kip Thorne here and Barry Barish here. The proposal is they're funded through the National Science Foundation, and they're going to remove one of those observatories. But you need both of the observatories to identify where things are coming from, in the same way that if you walk around with just one ear, it's very difficult. You hear a noise, but you don't know where that noise is coming from. Whereas if you have two ears, you can kind of triangulate the position of where something's coming. Or similarly with your eyes, if you walk around with one and you see a flash, you're like, where did that flash come? But with two eyes, you can use parallax to identify things and their distance. So without two observatories, it kind of removes the whole point of doing the thing. So anyway, there's definitely some shortcomings, and hopefully, again, I don't want to make this a huge political thing. I just want to make people aware of the consequences of the current budget, and hopefully there's still room for these things to change in the future with significant legislative pushback. Okay. Enough on a down note. Any other questions that we may have?
Thank you. This is for Ivy and Maggie on this. Let's say there's a massive solar flare, massive. What happens to Earth? What things go down? For example, electricity. Can you give us examples of what would go down if there's a massive solar flare? And for how long, possibly?
Ooh, doomsday.
Nothing good, but
So like a Carrington level event.
sure, yeah. So there's an interesting distinction between the flare itself, which is what we consider the electromagnetic radiation, the X-ray and the UV, and the coronal mass ejection that often follows these flares. So in terms of what's coming from the flare itself, that radiation, the X-ray, the UV, what you're going to get is a bunch of ionizing radiation at the top of the Earth's atmosphere. You don't get a lot of impacts on the magnetic field itself, but you might sort of dissociate like the ozone in the atmosphere, for instance. When the coronal mass ejection itself strikes the Earth, that's where all the fun stuff happens. That's where you start to get this magnetic compression. This is where you start to get fun chemistry because you're increasing the number of charged particles at the Earth, which drive a lot of interesting chemistry. And also, in the instance that it's strong enough, you can start to strip atmospheres, right? We're generally shielded by our magnetic field, but if it's strong enough, it doesn't matter. That material in the Earth is being stripped away. A fun consequence is actually the sun produces a lot of radio emission, which we don't tend to think about because it's a relatively low energy part of the spectrum. But in these instances where you have highly enhanced radio emission, you can actually very highly disturb things like GPS. It directly interacts with the electronics, and that messes with everything. But it's the particles themselves that interact and cause like a current that was responsible for causing telegraph stations to catch fire. It was the enhanced current caused by the introduction of extra charged particles. So yeah, nothing good. We have experienced similar things like the Carrington event in the past few decades. In particular, in the 1980s, there was an exceptionally strong coronal mass ejection geomagnetic storm that hit the Earth that caused a blackout across basically, I think, most of Canada, and dealt extreme damage, exceptional amounts of money to repair. So yeah, we don't want it happening.
Yeah, so as a follow-up, we've been talking a lot about stellar outflows, and it turns out that the most massive stars, so stars with masses of more than 10 solar masses or so 10 times the mass of our own sun, end up having a lot of, or emitting a lot of ionizing photons, as Ivy mentioned. And if these stars are rotating very fast too, they end up losing or shedding a lot of their stellar envelopes. And so most of the planets that you'll find around stars are actually around lower mass stars, and also habitable zones are usually around these lower mass stars, or it's easier to have habitable planets around lower mass stars. And one reason is because you have a lot of stellar outflows from these massive stars.
There was a follow-up question to this online, and that was, is there anything that we can do if we know that a Carrington event is on the way, either through the flare, but also through the coronal mass ejection of material that's streaming towards us and is going to take a couple of days to arrive? Is there something that we can do to like hunker down? You know, when you know a hurricane's on the way, can you get in that storm shelter and do something about it?
Turn off your electronics.
Yeah.
This is one of the reasons why things like NOAA, the National Observatory for Atmosphere, is so important, is because it says this type of event is about to strike us, and here's how you prepare your power grid for it. I don't deal a lot with the intricacies of electrical grids, but we do have essentially fail safes in place in the case that we predict that an extreme event is about to strike us. We can prepare our electrical grid so that we don't experience trillions of dollars of electrical damage.
Yeah, did you say it's long lines of power lines that basically pick up current, and so you can basically break those up and then hopefully disable those huge currents. Okay. Additional questions? Oh, you've got your notepad. Uh-oh.
So I threw you a hardball earlier. I hope that this one's softer. Are there lists of calculations for how much ozone we're accumulating over time? If we're accumulating particles in the belts, then the logical theory might be that we're also accumulating more ozone over time, and that has specific events or implications for some applications.
So what I do know about chemistry is that actually one of the signatures people look for as a sign of life is a presence of both ozone and oxygen, because in the absence of life, you do build up ozone. But because we're here on Earth, we are interacting with the atmosphere in a non-thermal equilibrium sort of way, which is to say we're being weird with the atmosphere, that we can sustain both oxygen and ozone, so we don't get this surplus of ozone essentially.
Question back here.
Hi. So my question is, since NASA made wrote a theoretical thesis of making artificial I can't even say that word, electromagnetic field around Mars, so it deflects radiation from the solar flares and solar storms. So is it possible that we have like, if Earth or we make something that deflects solar storms and solar flares on that matter?
Yeah, so the question is referencing, okay, in the idea that we might want to go to Mars, there's a lot of proponents of occupying Mars or whatever, of going to Mars, but this is like something worth asking. But as Ivey discussed, Mars doesn't have much of a magnetic field, so it gets impacted by these flares, and so it would be bad for us to go there because we'd get sort of, coronal mass ejections and solar wind interacting with us. So the question was referencing, there was a proposed idea of building a structure that co-orbits in front of Mars, sits between Mars and the sun, and has its own strong magnetic field that shields us over time. You didn't talk about this in your presentation, did you?
I did not. This is news to me.
Okay. Okay. I just didn't want to be stepping over you because I was paying attention for most of it, but I wanted to make sure I didn't miss something. So, so the idea is that we have this structure that has a strong enough magnetic field that it acts as the shield that shields Mars in the same way that the Earth's intrinsic magnetic field shields us. So this was actually proposed by the head administrator of NASA about 5 or 10 years ago. Yeah, okay. Yeah, it was a bit ago. That's right. So this is possible. It's expensive to do.
On Earth, or we make another one in order to counter these attacks. More flares we get, the more electrons, since we're going into AI machine learning.
We're definitely more reliant on electrical systems than we have been in the past. Sure.
So, and what NASA only has right now is a protection website telling you 30 minutes beforehand. Oh,
I'm just making sure the online audience.
Okay. Beforehand, so that they could, 30 minutes in advance that that there's a solar flare coming. So I'm sorry. So if it's possible that, so what I'm trying to say is that it's either making a protection or seeing that if this hypothesis actually works, but with
Yeah, I mean, it should work. It's just very expensive, and coupled with that we're seeing a drop in the funding for NASA by 50%, I think it's unlikely that we're going to bolster a bunch of money towards building some sort of hypothetical magnetic shield for the Earth. I agree with you that this is a good idea, but there's just a lack of funds for doing it. But it seems like, we understand electricity and magnetism reasonably well. That we've had it around we've well understood it for like 150 years. And so I think this makes sense that we should be able to do this. You have more to your question? Every possibility of what's going to happen with a magnetic field moving out from the sun?
As in a hypothesis of making some action like venting.
The coronal mass ejections. Is there a way that we can use machine learning to predict every way that a coronal mass ejection will come off the sun and then block it? Maybe. I find that our understanding of AI and machine learning gets very overblown in the media, that it's doing all these things that it's not yet capable of or may not ever be capable of doing. And this, I think, is one of those examples. I think we can certainly run simulations for how we think coronal mass ejections might be lifted off the surface of the sun and moving stuff into the outer solar system, but we don't yet. Much of the reason for the work that Ivey is doing, as well as other heliophysicists are doing, is to try and understand the complicated magnetic field on the sun and how we can look for signatures that will let us predict, kind of like we want to know when an earthquake's going to go off. So we have to, put seismographs all over the place and try and understand from those sensors, something predicting that sort of thing. It's the same thing with the work that heliophysicists and astronomers like Ivey are doing. So we need to be able to understand that, and then either have some sort of machine learning or even not machine learning that takes those inputs and makes predictions for what's coming out, but we don't yet have that. And that's what we're trying to work on. Right?
Mm-hmm.
Yes. Okay.
Just to add on, AI machine learning is regularly incorporated into astronomy, often as a way to identify signatures, not necessarily to build hypotheses. So we do regularly use it for identifying, for instance, something that's really relevant to my work are radio signatures associated with solar energetic particle events, which are highly associated with coronal mass ejections. And one of the signatures of this are radio emissions that are very narrow in time, but very broad in frequencies. So having something that can sift through all of the data sets we have coming out of the sun, because we do still have all these missions. We have so much data. One singular human or even a collection of humans can't go through it all together. You need some sort of computational crutch to get through it all. So that is regularly incorporated, but I would say that hypotheses, a connection between the signature we see and what that means for the event, that is still very heavily human driven.
Yeah, well said. Okay. Additional, you have a question.
Is there a limit to like how much stuff is ejected from the sun? Like we wake up one day, like 8 minutes later, no sun. I don't know, like, do we know how big like it can get?
Ejecting its whole mass.
That's a question for you. Supernovae. Oh, sure. For the sun, well, you need some mechanism by which things are ejected. The sun, as it reaches its later stages of life, it will expand. It'll get more diffuse, less dense, and expand into where the Earth is. And this is driven by fusion basically happening at the center or near the center of the star, heating up the outer layers, and just to counteract the increase in temperature, the outwards pressure of the star will increase. And so you'll have just a bigger star. So in terms of like ejecting everything out of a star, you're going to have to look to higher mass stars for that to happen. So Ivy talked a bit about of like you have a bunch of different kinds of stars, different temperatures and masses. And so for a star with a mass like our sun, we won't undergo something like a supernova event where pretty much all of the like stars envelope is completely ejected, as what you're saying. Massive stars, though, will undergo supernova. And this is just because they have enough energy to explode the star and strip away the outer envelope in an explosive event. So in terms of our star, we're not going to undergo supernova, but we will, over time, our star will lose hold of its outer layers. But there are more massive stars where a supernova event can happen and eject out pretty violently its outer layers, leaving behind a neutron star or black hole.
And just to add on that, as alluded to by Maggie, our sun, late in its evolution, in about 5 billion years, when it runs out of hydrogen in its core to fuel its power, will shed those outer layers almost entirely. And I don't know, did any of you look through the telescopes? Did you see the Ring Nebula tonight? You did? Okay, so the Ring Nebula is an example of what's known as a planetary nebula. It has nothing to do with planets. That's just a misnomer. But it is a star like our sun that has shed its outer layers in some sort of massive, it's kind of like a coronal mass ejection, except it's the entire surface. Do we have a picture of it here? I think that's like an O star though. So it's shed its entire outer layers and they're continuing to drift away from the star and glow as they do. And so you can see it in the night sky. It's almost directly overhead in a couple of hours. It's called the Ring Nebula, and it's an example of one of these systems where it sheds the outer layers and you're just left with the core of the star there. And I should also mention, if you haven't looked at the telescopes tonight and you want to, they'll be operating for about 10 more minutes. So I encourage you to go outside and check them out if you want to look through them. Okay, next question. Did you already ask? You already asked a question. I'll get to you again, but I want to make sure people who haven't. You're a new voice. All right, Top Gun. There you go.
Thank you. So if each of you had to say one thing you're most excited about in astronomy or astrophysics the next 5 years, what would it be?
So I can speak for time domain astronomy. Time domain astronomy is when we look at the sky for signals that vary over time. I'm particularly interested in transient astronomy. So when you see something that brightens really fast in the sky and then dims, and you pretty much usually never see it brighten back up again. And so these events are associated with like a variety of different kinds of like stellar activity and stellar events. And a lot of our observations are very biased to the local universe because we're limited by how far and how faint we can see. And so right now, time domain astronomy has a lot of new facilities coming out. You might have heard of the Rubin space or the Rubin telescope. You might have heard of UVEX, Ultrasat. You have the Roman Space Telescope that's being hopefully launched soon. And so all of these different instruments are looking at different bands of the electromagnetic spectrum. And they're very sensitive instruments. You can look for very faint objects, and they're all designed for time domain astronomy. So you look at the same patch of sky pretty regularly or pretty frequently, and you scan over a large portion of the sky to catch these rare things that show up and then dim again. So time domain astronomy is pretty exciting right now.
Yeah, so I guess I'll go next. I'm very excited about the future of X-ray astronomy. And I'll tell you why they're laughing in just a minute. So X-ray astronomy is really exciting because it allows you to study the largest and the most energetic sources in the universe. And so our current X-ray telescopes, like the Chandra X-ray Observatory, that was the flagship NASA mission that Cameron mentioned a little bit earlier, it's been operating for 20, 25 years, has allowed us to study the most energetic events in the universe. And so the way that it operates is by using a detector that when the incident X-ray photons come in, we measure how energetic they are by the electric current that they produce in the detector, so by the charges that are generated. And this technology was well and good 20 years ago, but now we have a new type of X-ray detector, and this is called a microcalorimeter. So rather than measuring the energy of an X-ray photon from the electrons that it generates, we measure the change in temperature that that striking photon induces on the detector. And that allows us to get about 100 times better in resolution. And so rather than saying this photon is about this energy, we can say very precisely what energy this photon is at. And so we've increased our sensitivity in these detectors by about a factor of 100. And so if we put these detectors on the next generation of X-ray telescopes, you can imagine the increases in the amounts of new discoveries that we can make. And so I'm particularly excited about the next generation of X-ray telescopes, specifically those that have, these new detectors that will increase our resolution. So this allows us to study the hottest plasma in the universe. Not only that, we can get its temperature, we can study how fast this plasma is moving because we can finally say what energy these photons are really coming in at. And so these are missions like the European Space Agency has proposed and is working on building the Athena telescope, which utilizes this technology. There's a NASA proposal for a mission called LYNX, which I don't want to get into the funding politicalness, but it's very far off just because it's very expensive to do. The technology is there and it's very exciting, but there needs to be sort of this broad push from not only the astronomical community but also the public to say that this is interesting and this is cool. And there's a couple other missions that are in concept right now that also need a lot of support right now. So incredible technology, really interesting opportunity for studying the hottest plasmas in the universe, and needs a lot of support right now.
I feel like I would get in trouble with my advisor if I didn't say I was excited about the DSA 2000 or the Deep Synoptic Array 2000, which is an array of about 2,000 dishes. This is operating at low frequency radio or relatively low frequency radio. So you need multiple elements in order to both synthesize an image of the sky, but also to reach the sensitivity that you need in order to see a bunch of the fun things happening in the radio sky. And the DSA 2000 is sort of the first of its kind. It was using the long wavelength array, which is the instrument that I use, as sort of a pathfinder for this concept. But when you get enough elements of an array really close together, you can essentially take a picture of the sky in the radio the same way you take a picture of the sky in visible light. And this is an effort, a method that hasn't effectively been utilized before. So this is a really exciting method and instrument that's up and coming in the next few years. It's going to begin construction relatively soon. And speaking of time domain astronomy, this is going to be an incredible tool for imaging the sky, so much of the sky, so quickly, so that we can really effectively do time domain radio astronomy in a way that hasn't been achieved before.
The only thing I'll add are a couple of, you've heard a wide distribution of exciting topics from the rest of the panel across the wavelength bands of the electromagnetic spectrum, from X-rays to, I guess yours time domain was optical and all sorts of things, and then radio parts of the spectrum. I'll just add that there are a couple of upcoming telescopes that are coming online in the next month, as well as the next couple of years, that are very large. The Vera Rubin telescope will have its first results coming out in the next 2 weeks or so. We might have an event here, but it's going to be at like 8 a.m. on a Wednesday or something. So I don't think there's going to be a lot of people. I don't want to be here at 8 a.m. on a Wednesday. So maybe you guys don't either. But this is going to be a very large telescope that's taking images from Chile in the visible part of the spectrum and covering the sky quite frequently. Once every couple of days, it's covering the entire sky. So you get to see how the sky is changing over short timescales, a la what Maggie was discussing with time domain science. There's also a very large telescope that's being built primarily by the Europeans in South America. It's called the ELT, the Extremely Large Telescope. and it will be the largest optical telescope in the world. It is about 100 feet across. The primary mirror is about 100 feet across. So like, you know, bigger than this room across, like 3 times the size of this room. The mirror will be collecting all that light and bringing it down to a camera, a focus on a camera, so you can see very, very faint things. We here at Caltech, we're trying to build something called the TMT, the 30-meter telescope, but we just found out that it got basically canceled in the new budget. But at least the Europeans will be able to go forward with this, and it's going to be really sweet. So that's under construction right now, and we'll probably see first light in like 3 years or something. So anyway, a wide variety of answers for you. There's lots of exciting things coming out soon across the electromagnetic spectrum that will lead to new discoveries, I think. Yeah, so is there more collaboration in astronomy across nations, across institutions for these telescopes? So just because the Europeans are building it, does that mean that we won't have access to those data? Or yeah.
Yeah, so maybe I'll offer some thoughts and others can chime in as well. I found astronomy across institutes, across countries, to be extremely collaborative in nature. Particularly nowadays in astronomy, we've talked about all these wonderful telescopes all across the electromagnetic spectrum coming online. And there's only so much you can learn about an object that's, you know, a billion light years away by just using one telescope. And so you have to combine all of these different data sets to learn a variety of different things about the physics of your object. And that wouldn't be possible if you didn't share your data, if you didn't make it accessible, if you didn't make it usable. And so not only I think is that encouraged, but in the modern age of astronomy, it's necessary. And more, we're not just talking in an observational sense between telescopes, between different universities. We're also talking about the intersection of observational data with computer simulations, like we were talking about earlier. So sometimes we'll take an observation with a telescope and we won't understand what we're seeing. So we'll get some more data on a different telescope and it'll look even weirder, right? And so the only way to really understand that at that point is to make a hypothesis and to test it with simulations run on a big computer. And oftentimes those simulations are now becoming more and more public and more applicable to, you know, observational data sets. And so it's really becoming an extremely collaborative field where it's really necessary to combine all of these different tools that a variety of different people will sort of make accessible.
To give you an idea of what happens when we discover something pretty interesting, so we have a Slack channel, and people are all like over the world are in the Slack channel. People from Stockholm, from India, some people from Thailand, China, and we are like, okay, how much telescope time do I have, and can I give some of that to observe this object that we're looking at? So we trigger a bunch of different telescopes all over the world to look at this particular object, and we use people's telescope time. So people actually, to observe things, we need to propose for time on these different telescopes, and you may or may not get that time. And so you really need to corroborate everyone's allocated resources to look at this one thing.
They gave a really great summary, but I'll just say from current experience, the instrument that I primarily work on, the long wavelength array, is an instrument that is operating under the combined efforts across many institutions across the United States. And I'm currently involved with multiple proposals with folks here at Caltech, but also JPL and also at CSIRO in Australia. People really like the sky and it's so easy to share. So science only gets better when you share. And I think generally astronomers have identified that.
There's a lot of sharing. Because for the most part, it's proprietary when we get data, depending on the telescopes. And there is competition because people are like, I got to make a name for myself. I got to put out a paper and so on and so forth. But we're also not dealing with stuff that's spycraft or that's going to result in people, for the most part, people dying here or there. So, you know, you have to keep this all in good context. Like, oh, I want to work with that person over there because they're smart and they're nice and they could help my project along. And we could, you know, ultimately people go into science not to make money, but because they want to better understand the world around us. And so usually you can better do that in teams and working with collaborators at different institutions in different countries. So there's a lot more collaboration than you might find in banking or something where the high stakes are high to make money or whatever. I think it's both the people who are involved as well as we're just all trying to figure out how the world works. So, question, but I promised an online person the answer to their to ask their question. Can gamma ray bursts from supernovae or gamma ray bursts and supernovae disrupt Earth's electromagnetic field or represent a threat to life here? If a gamma ray burst is shooting right towards us, or if a supernova is too close to us, what do you
That
think?
would be pretty bad.
It'd be pretty
Yeah,
bad.
that would be
yeah.
pretty bad. Even like a supernova, say a parsec away or so, which is around
3 light years.
3 light years, yeah. That can significantly dissociate all of the molecules in our atmosphere. I actually did a homework problem on this like 2 weeks ago.
Nice.
And that, you know, has significant impacts on the chemistry and the atmosphere that we breathe. Gamma ray bursts are some of the most energetic events in the universe. And to give you an idea, the energy that they output is around 10 to the 40. I don't know if that's actually like supernova level scales within a really short time frame. So you get this huge influx of energy in a really short time frame. If that were pointed to us, you know, bad things would happen because there are gamma rays in a gamma ray burst. And I feel like I've heard that one of the major mass extinctions on Earth is like consistent with a gamma ray burst event pointed toward us.
I haven't read that.
Yeah, Ivy might know, but I'm not.
Do you know about it?
Sure.
I've also heard about it, but it's hard to date things
It's hard to
appropriately
date
when you go
things.
back that far.
Yeah, sure.
Yeah, but you know, something that's nice is that a gamma ray burst probably wouldn't happen pointed toward the Earth. That's close enough for us to actually feel the effects. And this is due to a variety of reasons. One is gamma ray bursts occur in these really thin collimated jets. And so it's just unlikely for you to, or for the Earth to be situated into one of those collimated thin jets. So that's one reason. Another is that most gamma ray bursts happen, at least on stellar gamma ray bursts, they happen in the very early universe. Because of physics reasons, metallicity, massive stars are easier to form in the earlier universe, X, Y, Z. And so for those reasons, we're probably safe from a gamma ray burst.
Oh boy. Okay. Well, that's good. That's good. Okay. There's a question here, and then I'll ask some more of the online questions.
So until your lecture, I did not know that Mars did not have an atmosphere. And
it does. It's just really
well, yeah. So I was just wondering, like, in The Martian, when he like grows, but like, can you do that? Like, can that? Is that total fiction, or could that happen? Could you grow potatoes? Could you live and breathe?
So I've seen The Martian once, maybe a decade ago, but my understanding was that Mark Wahlberg, Matt Damon.
That's not Marky Mark.
Not Marky Mark.
Not Marky Mark.
Was growing these potatoes in a shielded environment, right? So similar to the way the ISS, International Space Station, is shielded in certain regions, or extra shielded in certain regions to protect the astronauts on board. Matt Damon was growing these potatoes in a protected environment that they weren't going to be directly impacted by all those energetic particles coming from the sun. So in principle, if you have a shielded enough environment, you could do this. It's very expensive to get that materials to Mars and then to maintain the upkeep because Mars actually has a pretty substantial winds, even in the absence of an atmosphere, all this dust that gets blown away, which I believe was a matter of contention for Matt Damon in the movie too.
Yeah, so agreed. It's not Mark Wahlberg, it was Matt Damon, but it's a contained habitat that they build on Mars. So he's not just walking around on the surface without his helmet on, because that would be bad. The atmosphere is very low density, the pressure is low density, you'd suffocate and die. So he's in a suit, but then he builds a little habitat with his Martian crewmates. They build this habitat, and it's an enclosed space, like a room like this. And then they change what the atmosphere is like in that room so he can take off his thing and so that you can grow these potatoes. So the interesting thing about The Martian is that book was written by a guy, but in the early stages, he kind of crowdsourced the ideas in the book. So he'd write out a version of a chapter or something like that, and then make it available to people online who could comment on how accurate, or if there were holes, scientific holes in the storyline that were wrong, and then he'd correct those things. And so it's really interesting. It was basically like an open source book that he wrote and provided to the community, and other scientists like me were reading that and providing guidance with how he could change the plot to make it better. And so the first version of that book that came out was a text file that you could download for free online. And eventually, and I have that text file on my computer because I was one of those early people reading this, like chapters of this book. And then eventually he, had this great novel, and then was approached by a publishing company that was like, we want to publish your book. And then they made it, and then you have to buy it, and then it was turned into a film. But for that reason, almost all the science in that book is actually pretty accurate, because it's been already vetted by scientists to make sure that it's accurate. Not the one scientific kind of drawback to that film. Again, we're talking about spoilers. People who are like, what the heck is The Martian? Sorry. But one of the first things, when there's the storm that happens on the surface of the Mars, which leads his crewmates to flying back because the storm is going to push over their rocket, the density of air on the surface of Mars is so low that you don't have storms that are that forceful that you could push anything over, because there's just not enough air. There's not enough pressure that you can push something because it's so low density. So that's the only thing that's kind of inaccurate, but you can give it a one free, get out of jail free card, and the rest is pretty accurate. So for what it's worth. You have a follow-up question?
Slightly unrelated topic. You earlier at the beginning, you were talking about how there's a lot of helium-3 on the moon.
Yes.
Could helium balloons float on the moon?
Could helium balloons float on the moon? Well, the helium-3 that's there is deposited in grains. It's not just floating around like the helium that we have here. The helium that we find on the Earth is usually trapped in not balloons, in the interior of the Earth. And we basically, because it doesn't, oh man, so much to talk about with helium. Helium is an inert molecule, so it doesn't really interact well and form other molecules. Because it doesn't have any valence electrons. And so you typically find helium in its like native state in gaseous form in the interior of the Earth. And they like grab this and then put it in balloons or whatever you need it for. But once it's exposed to the atmosphere, it just floats up. The helium-3 that's on the surface of the moon, I don't know. I think it's trapped in vesicles in the rocks or something like that. I think it's on a molecular scale, and so extracting it could be potentially hard. But in terms of your actual question, would helium balloons float on the surface of the moon? I mean, do things float in vacuum? Is there still buoyancy? I don't think so. No, there's no buoyancy, so there's no atmosphere. So a helium balloon would just fall to the moon's surface and be like, meh, meh. So it's the same thing like the Apollo astronauts. They dropped a feather and they dropped a rock alongside each other, and in a vacuum that it was predicted by Isaac Newton and gravitation that these things without air resistance would both fall towards the surface of the moon at the same rate, and they did. And you can do this experiment too if you if you stick a feather and a rock in a vacuum tube and evacuate the air resistance and drop them, they'll both fall at the same rate. So I think it should be the same thing for a balloon, shouldn't it? There's no buoyancy. It's not displacing any other atmosphere. There's no atmosphere, so it should just fall. Probably fall and then bump up against a rock and then burst and then. But I think that's what it should do. Oh man, now I'm on the internet saying something. Hopefully that's correct. It seems like it should be correct. But all right, we've got. Do you want to add to that? You've got your mic, so okay. There was a question online I promised I'd get to, and that was, why does Venus's electromagnetic field differ from Earth's, but still sustains its atmosphere unlike Mars? So Ivey talked a little bit about this earlier. Mars and Venus, neither of them have magnetic fields. So why does Venus have an atmosphere and Mars doesn't? I think it's just because Venus is replenishing it so much. It's like got all kinds of gaseous outflows from the surface that are replenishing it. If those stopped, then the solar wind would blast it away and it wouldn't have an atmosphere, but it's constantly replenishing it, right?
Yeah, and to elaborate on that a little bit more, the reason Mars doesn't have a magnetic field, we hypothesize, is that it's smaller than the Earth, so it cooled down faster than the Earth. So for the Earth, our magnetic field comes from a really hot interior rotating, and that generates what we call a dynamo effect that produces a magnetic field. But like the moon, Mars is too cold to maintain that internal current to produce that magnetic field. Venus, on the other hand, is not producing a magnetic field because its rotation is weird, which is the other element for producing a magnetic field. But as you were saying, it's pretty volcanic. It is constantly outgassing things from the interior to it because it is about the size of the Earth. So it's still pretty warm and nearly said magnetically active, but magmatically active.
Magmatically active. Yeah, that's right. More questions? You've any people who haven't asked oh goodness, something's going on out there. Any people who haven't asked a question yet have a question? Oh, aha, okay.
So I just had a question with I guess increase in like satellites going up. How much does space weather or solar flares really need to be considered in like causing damage to those and maybe extra like risk in like collision or creating some kind of space trash? And I don't know, how do you think that would, if that is relevant, how do you think that would impact putting more satellites up and maybe even modeling for like additional like risk of collision?
So for sure, the winds and solar activity have a pretty big impact on the sustainability of a satellite out in space. I think we actually see that HST that's been in orbit since the 90s has a pretty substantial curve where it gradually deorbits when the sun is most active. So it plays a pretty big impact in the orbits of these satellites. And of course, the electronics, a high energy particle hitting a detector is going to hurt the detector. Yeah, that said, I think as we put more satellites out into space, the satellites are doing a lot of damage to astronomy as well, especially in the era of time domain astronomy, where we see these satellites just streak across our images. So there's a twofold effect in terms of our understanding of astronomy through these satellites, and also those satellites impinging upon our understanding of astronomy.
Okay, we've come to 10 o'clock. There's one last question that I promised somebody online that I'd answer. Emily's got an alarm going on. The question is, when galaxies are constantly absorbing other galaxies and they're supermassive black holes, how do they retain their shape? How does a galaxy retain its shape over very long timescales if it's constantly merging with other galaxies? And what happens to all these supermassive black holes from the other galaxies that are merging with our own galaxy?
This
You
is
wanna
a
talk
question
about
about
it?
merging supermassive black holes.
Well, both merging supermassive black holes as well as merging galaxies. How do galaxies retain their
sure.
shape over time, or
Yeah.
or don't they? Or
Yeah, so this isn't necessarily something I'm an expert in, but I think one of the key things when you consider galaxies merging is that galaxies are made up of a whole bunch of different things. And so, in particular, the way that I like to think about a galaxy is it's sort of this spherical-ish halo of dark matter, which is this type of matter that we think exists in the universe that doesn't emit light like normal matter does, but we think it exists just because we've observed its effects in multiple places and ways. And so most of a galaxy is actually dominated in mass by this halo of dark matter. And then inside that halo is a bunch of, if you consider a disk galaxy, so that disk is then filled with lots of gas and lots of stars. And the gas and the stars behave in somewhat different ways. So if you have two galaxies that collide with one another, their dark matter halos are going to collide together, but we think dark matter only really interacts under the force of gravity. And so those two halos are going to largely pass through one another. But the really interesting thing is going to happen when we consider the gas in the galaxies. So if you imagine like two clouds ramming together, they're not going to pass right through each other, right? They're going to hit each other, and there's going to be a bunch of really cool stripping and things that can happen. And it's similar to the gas in galaxies. And you might ask, well, what about the stars, right? We look up at the Milky Way and we see all these beautiful dust lanes, all of this glowing gas, but we mostly just see the stars. And the stars are really cool because when two galaxies merge together, the stars are somewhat collisionless just because the galaxies are so big, their dark matter halos are so massive, and the stars themselves are so small. And so the frequency of, star to star mergers as two galaxies are colliding is relatively rare. And that means the stars actually behave somewhat like the dark matter, just because the dark matter doesn't collide with itself. So they're really interacting via gravity. And so a lot of the cool effects that we see when galaxies merge together is due to that gas colliding. And so when two galaxies merge together, as all of that matter strikes together, it's going to get hot. It's going to start to disrupt the shape of the galaxies. So if they were spirals, they'll then be spirals with a bunch of weird things sticking out. They'll have sometimes tails of gas streaking here and there. And because that gas is supplying the fuel for which the stars form. So the gas, as it cools, will form stars. And as galaxies merge together and that gas is heated and disrupted, it's going to affect the rate at which the stars are formed. And so that's going to have some effects. In terms of the supermassive black holes, which is the question I'm actually afraid to answer here, maybe Cameron has some thoughts on what the supermassive black holes do.
I mean, they will merge together for the most part. If you've got this galaxy and this for instance, in the future, the Milky Way will eventually merge together with the Andromeda galaxy, and the supermassive black hole in the center of the Milky Way will merge together with the supermassive black hole in the center of Andromeda. And we see evidence for this with the LIGO instrument detecting mergers of black holes through gravitational waves. But yeah, gravity brings two things that are very massive towards each other, and eventually they form. We don't understand in detail the actual mechanism by which they form together, but we understand that it must happen. So,
and it's going to release like a huge amount of energy, right? So there's going to be tracers in the X-ray and all different sorts of wavelengths
and gravitational waves.
Yeah. And so it's going to affect the state of the galaxy and how it can form stars and what it looks like after that, for sure.
And I should allude to our previous panelist, Gene Samowar, gave a presentation all about black holes and how they feed on their neighbors and other members of their tribe. She gave this presentation just a few months ago, so it's on our YouTube channel if you want to learn more. Okay, thank you guys for all sticking around. Thank you, YouTube audience. We will be back. Our next event of these will be in the middle of July. I'll set the date and I'll put it online. It'll be all about the formation of our solar system and how it has occurred and how it is today and how unique that is to other stellar systems. And our next Astronomy on Tap is in just a few weeks on Monday, June 23rd, all about black holes. Thanks for joining us. We'll see you guys next month.